Elements contain only one type of atom, for example, hydrogen and chlorine. Compounds contain two or more elements chemically bonded, like when hydrogen and chlorine combine to form hydrogen chloride. Mixtures contain two or more substances not chemically bonded. The substances therefore can be separated. This is the periodic table. It arranges elements based on similarities in their properties. The vertical columns are called groups and the horizontal rows are called periods. Structure of the atom. Protons and neutrons are arranged in the center of the atom, forming the nucleus. Electrons orbit the nucleus in shells. These are the relative charges and masses of a proton, neutron, and electron. The relative charge of a proton is positive 1, neutron is 0, and electron is negative 1. The relative mass of a proton is 1, neutron is 1, and the mass of an electron is extremely small, close to 0. Proton number or atomic number is the number of protons in the nucleus of an atom. Mass number or nuclear number is the total number of protons and neutrons in the nucleus of an atom. Electronic configuration shows the arrangement of electrons in an atom. The first shell can hold a maximum of 2 electrons, the second shell can hold a maximum of 8 electrons, the third shell can hold a maximum of 8 electrons, and so on. This is an example for the electronic configuration of chlorine. First, identify the number of electrons. In this case, the number of protons equals the number of electrons because it is an atom, so there are 17 electrons. Draw the electrons starting from the first innermost shell and going outwards. Notice that the electrons are paired from the second shell onwards. To write the electronic configuration, state the number of electrons in each shell from the inner shell separated by commas. Using this electronic configuration, there are 3 numbers, which tells us the period number and the number of occupied electron shells. The final number is the group number, or the number of outer shell electrons. Therefore, the group 8 noble gases will have a full outer shell. Isotopes are different atoms of the same element that have the same number of protons but different number of neutrons. When writing atoms, this is the common notation used. The symbol of the element goes on the right with 2 numbers. The bottom smaller number is the proton number or atomic number. The top larger number is the mass number or nuclear number. Ions look similar, but there is a charge on the top right of the element name. In this case, chlorine has 17 protons, but since it has a 1 negative charge, it will have 18 electrons. That is, it has 1 more electron than proton. Isotopes of the same element have the same chemical properties because they have the same number of electrons and therefore the same electronic configuration. Why? Let's say we have an atom carbon-12. It has 6 electrons, 6 protons, and 6 neutrons. Carbon-14, which is an isotope of carbon-12, also has 6 electrons, but it has 8 neutrons. Therefore, the electronic configuration of both isotopes are 2-4, 2 electrons in the first shell and 4 electrons in the second shell. Therefore, they have the same chemical properties. Calculating relative atomic mass. Relative atomic mass, notated AR, is the larger number seen on elements. The formula to calculate it is mass of isotope A times percentage abundance A plus mass of isotope B times percentage abundance B divided by 100. Let's take an example. The relative masses of isotopes and their abundances, which is how common it is to find it, of boron is shown. To calculate the relative atomic mass, do 10 times 20 and add it to 11 times 80. Divide by 100. The answer is 10.8. Positive ions are called cations. When an atom loses 1 electron, there will now be a positive plus charge. When it loses another electron, the charge becomes 2 plus, losing a third electron makes the charge 3 plus, and so on. Negative ions are called anions. When an atom gains 1 electron, there will now be a negative minus charge. When it gains another electron, the charge becomes 2 minus. Gaining a third electron makes the charge 3 minus, and so on. An ionic bond is a strong electrostatic attraction between oppositely charged ions. This is an example of ionic bonding. Sodium, or Na, has 1 electron in its outer shell. It loses that electron to become stable, forming an Na plus ion. Chlorine has to gain 1 more electron to become stable. The electron lost from sodium is gained by chlorine, making it a Cl- ion. Notice that different ions are differentiated with dots and crosses as electrons. The resulting compound is NaCl. The positive ion is written first, followed by the negative ion. No charge is written in the compound name. This is called sodium chloride. Chlorine becomes chloride when it becomes an ion. This is another example. Magnesium, Mg, has 2 electrons in its outer shell. It loses those 2 electrons to become stable, forming an Mg2 plus ion. Each chlorine atom gains one electron to have a full outer shell, each becoming a Cl- ion. The compound is MgCl2 because there's one magnesium and two chlorine atoms involved. This is called magnesium chloride. Again, chlorine becomes chloride when it forms an ion. Properties of ionic compounds. Ionic compounds have high melting and boiling points because ionic bonds are held together by strong electrostatic forces of attraction that are between oppositely charged ions. Good electrical conductivity when aqueous or molten, as they are free mobile ions, but poor electrical conductivity in the solid state. Ionic compounds are also soluble in water. A giant ionic lattice is a regular arrangement of alternating positive and negative ions. The diagram shows what this looks like. The positive ions are Na plus ions and the negative ions are Cl minus ions. Most ionic compounds look like this in the solid state. A covalent bond is formed when a pair of electrons is shared between two atoms, leading to noble gas electronic configurations. These are some examples of simple molecules. Hydrogen, H2, shares one pair of electrons between two hydrogen atoms. Chlorine, Cl2, shares one pair of electrons between two chlorine atoms. Water, H2O. Methane, CH4. Ammonia, NH3. Hydrogen chloride, HCl. Methanol, CH3OH. Ethene, C2H4. Oxygen, O2, shares two pairs of electrons. Carbon dioxide, CO2. Nitrogen, N2, shares three pairs of electrons. Properties of molecular compounds. They have low melting and boiling points because of weak intermolecular forces of attraction between molecules. Although there are strong covalent bonds between the blue and purple atoms, there are weak forces between molecules, shown by the dotted lines. Molecular compounds have poor electrical conductivity because there are no mobile electrons. Molecular compounds are also insoluble in water. Let's look at some examples of giant covalent structures. This is diamond. In diamond, each carbon atom is covalently bonded to four other carbon atoms, forming a tetrahedral shape. Diamond is extremely hard because of this bonding and therefore is used as cutting tools. Diamond has a high melting and boiling point due to strong covalent bonds, and poor electrical conductivity as all electrons of carbon are shared. This is graphite. In graphite, each carbon atom is covalently bonded to three other carbon atoms, forming a hexagon shape. Graphite has a high melting and boiling point due to strong covalent bonds. It is soft and slippery due to the presence of layers, and has good electrical conductivity because of mobile electrons. Therefore, graphite can be used as a lubricant due to the layers, and as an electrode due to its good electrical conductivity. This is silicon 4 oxide, SiO2. Each silicon atom is covalently bonded to four other oxygen atoms, while each oxygen atom is covalently bonded to two other silicon atoms. This is shown in the bonding diagram, where each black line represents a shared pair of electrons. Silicon 4 oxide has a high melting and boiling point due to strong covalent bonds, and poor electrical conductivity as all electrons are shared. Metallic bonding is the electrostatic attraction between the positive ions in a giant metallic lattice and a sea of delocalized electrons. Visually, this is what metallic bonding looks like. The pink circles are the positive metal ions, and the yellow circles are delocalized electrons that move through the structure. The positive ions are arranged in layers on top of each other. Properties of metals. Metals have good electrical conductivity because the delocalized electrons carry a charge. Metals are also malleable and ductile. Malleable means it can be bent into shape. Ductile means it can be drawn into wires. This is because the metal has layers that can slide over each other.